what I'm going to do is give you a little introduction to the association of AlanDick and Jampro, which I didn't even know about when I traveled 80 miles down the road from where we had moved to be by our grandkids in the San Francisco Bay Area, and found out how close I was to them physically. And of course, I've known Alex and guys over there for decades, so it's kind of a fun semi-retirement gig to play with those product lines with the DTV Repack coming up. So as we've given this presentation and kind of travel around the world with some of the stuff that AlanDick's done, all DVB-T2 oriented, because that's how the rest of the world has rolled. We're just now catching up to that with ATSC3. A tremendous amount of experience and historic sites that they've installed and are operated on. He's going to wrap that up with a SFN in Singapore, which is an amazing story as well, kind of foreshadows what can come down here. So I'll give you a couple pages before I hand it over to my friend metric Ben Crease. See, when you come from outside the US, they believe in metric, so you're going to get all your tower heights in meters. Now, do I click this here, or am I telling somebody to do it? I click it here just with a downstroke. All right. We're going to talk a little bit about the business end of this as to who you're trying to transmit to with ATSC3, some of the business things that are now open to us, of course, that ATSC1 was throttling us back to. And of course, with the focus on ATSC3 here and Mark Richer being here, I think we all have a great appreciation for this new era of business possibilities, which is going to be the financial driver to ATSC3, and it's truly phenomenal. So we're getting ready for that, and then alongside that comes SFN as to how you got to put higher signal strength to places to compete with mobile media that's working with distributed antenna systems and things. We're not going to get a free ride like they are. I guess I foreshadowed myself a little bit here, jumping ahead to the AlanDick Association. I've had a lot of comments and nobody had any idea of this. So we're putting both logos now on things, and we'll give you a little worldwide tour of that. I'm going to turn it over to Ben and give you a little tour through the more precision of the megahertz and gigahertz and bandwidths and so forth involved in. My metric friend, Ben Crease.
Thank you, Mark. Thank you, Dave, as well. So I'm going to talk a little bit about what I call the digital application. A lot of the early slides are regarding ATSC3, but really any COFDM standard. So a lot of the slides that we saw yesterday from Gerard and the ATSC3 people are quite similar. And the thing to notice here that whilst ATSC3 is the first time in the US that the broadcasters have a COFDM signal, many places in the rest of the world have been doing this for almost 20 years. I remember installing the first DVB-T combiner in Crystal Palace in London, which serves about 20 million people, almost 20 years ago to the day. And so whilst some of the concepts to US broadcasters are very new, from a worldwide point of view, there's things that's not identical, but there's things that are relevant. And so the message there is we've had a lot of experience in some of these issues for many years. So in terms of the digital, one of the things we can do when we use ATSC3 or DVB-T is we can target different devices that can receive the signal. So as we saw yesterday, for example, you can have fixed reception, which is your typical kind of analog model, or we can do portable outdoor or portable indoor. And I think actually yesterday they also had fixed indoor, which I guess is more for the rabbit ear, the second television at home, as a fourth scenario, if you like. But I think this kind of choice was very much written maybe 20 years ago, where people just didn't have so many devices, so many television sets. We certainly didn't have, we didn't all have smartphones covering that. So in these different scenarios, in terms of what we need to do to make the system work, the network work, is we do need different RF levels because we have different local conditions. And So this was a typical scenario with a fixed reception. The exact numbers maybe vary according to the exact standard, but this is for an example. You have you know, a receiving antenna at 30 feet, and you have a receiving antenna which has a level of gain, approximately 10 dB gain. And so you need, in this example, at UHF, about 56 dB microvolts per meter for the system to work. And you'll notice this is from DVB-T, so this is an old standard, but the way the different types of audiences and the effect that it has on what you need for the signal is pretty much the same, because it's all based on a CFDM modulation. So these are the other two scenarios. You have a portable outdoor reception, and you have portable indoor reception. So on the portable outdoor, a couple of things happen. You lose height, because we don't tend to drive around or move around at 30 feet high. We tend to be on near the ground level. And also because now you don't have a fixed reception, and you're mobile, you don't controlling the direction of receiving the antenna is a problem. So you really need an omnidirectional receiving antenna. So you lose any gain there. And so when you put those two issues together, you're about 20 dB down, or you need 20 dB more to get the same network to work. And then if you come indoors, there's obviously there's building loss, and that could be anything from extremely high to something reasonable. But as a conservative estimate, maybe 10 dBs. So if you're using the same kind of model, and you want to have a system that's going to work on portable indoor reception, you need 30 dB more signal. So that's 1,000 times the signal. And it's probably unlikely that you're going to get mandated to have from a megawatt ERP to a gigawatt ERP. That's probably not going to happen. So the reality is like you need another way to get that signal level required. And again, this is just reiterating all these standards worldwide. The most prevalent one is DVB-T or T2. And obviously you have ATSC3 going to, coming soon to the US. Obviously South Korea's rolled some of that out. And you have some other standards worldwide, but again, the key thing is they're all OFDM signals, and they're all based on that technology, which allows you to have a single frequency network in a way that's very integral to the way that works. One of the things that was talked about yesterday is that you can have different modulation parameters, which allows you to have greater capacity. So you have greater payload in your capacity, or you can have a more robust signal. And then the other things that were also mentioned were like Doppler performance. So if you've got a fast-moving handset, obviously you need to account for that, or the size of the coverage that you can do in an SFN. The key thing to notice on this is for a given, I guess in this case of ATSC3, for a given pipeline, you can only pick one scheme, and it's kind of tuned to one particular way of doing things. So if you have a very mobile signal, you want better Doppler performance. If you have a signal that's in high noise, then you want a more robust signal. If you want to do a high definition 4K, 8K signal, you want maybe the higher bandwidth. So all of those are possible within these standards, but not at the same time in the same pipe. So yeah, these are the choices in terms of the different things. So every dot is a modulation scheme that can be used. So on the right you have much higher data rates, and on the left you have a much more robust signal. The interesting thing to note there is obviously ATSC1 you had a choice of one, excluding the single mobile standard. But the main thing to notice is that at the same data transfer, you don't need so much signal to noise ratio. So what that also shows is that ATSC3 and also DVB-T it's a better modulation system in terms of being more resistant to noise generally. So it's a better standard to use, and it also allows, as a broadcaster, to have many different modulation schemes to tune for whatever they want to do for their particular network. The thing with ATSC3 that's more of a benefit than any of the older CRFDM signals is within a given pipe you can actually pick different modulations. So you can, within your same 6 megahertz channel, you can have a signal that would focus on higher data rates, then another on high mobility, etc. And that changes the coverage area, because as we've seen, you need different field strengths for the network to work, or you make a more robust signal, so you don't need so much field strength. So you can pick the different modulations to suit what you want, which was going to change your network size. The other thing that a CFDM signal will help you with is if you employ a single frequency network. Again, this is about efficiency. You can cover your service area in a more efficient way, where you can have the level you need, the RF level you need to cover everywhere on all of the different types of systems that you need, whether it's fixed, mobile, etc. And I think efficiency is the key. We see here our spectrum is being constantly squashed, or we have to share it with many other people. So one of the ways that we have to cope with that is to have the most efficient system that we use in our industry. Otherwise, we'll be left behind. So in terms of implementation considerations, if we're in a situation now where we have our systems, some of the things that I'm sure we've all been considering with our 399 forms very recently is structural capacity. Does the tower have capacity? Does it have space? And in terms of our RF capacity, do we have power rating? Do we have bandwidth? Or is it a single channel system? So do we have to change our antenna or our transmitter because it's a different frequency? One of the other things that occurs when you have a CFDM signal compared to, say, 8VSB, is the voltages that are generated, the peak voltages that are generated, are higher. So there's anywhere between 8 dB to 10 dB peak to average for ATSC3. So what does that mean? It means that you might find that where before you were looking at a power rating would be your limiting factor, you might now find that voltage is your limiting factor. So instead of melting, it's going to arc over. And so these are some things that from the passive RF side, and on the transmitter side, obviously, that's a different consideration, a different design principle to look at in terms of your breaking point. So again, we've been working with this CFDM signal and higher peak to average ratios for many years. So we have appreciation of how that works. And the other thing is it possible to combine channels? Because we have less and less spectrum, and we have a situation where probably we're going to have to transmit ATSC1 and ATSC3 at the same time. So having systems that are more broadband and that can combine frequencies gives you more flexibility going forward. And another thing that I'm just going to touch on is elliptical or circular polarization for mobile devices. Having an element of vertical polarization in your antenna greatly increases the probability that in a mobile situation, particularly if you don't have line of sight, that you will receive the signal. Essentially, because a mobile device, the polarization of a mobile device is anything. It's whatever it is. Probably study shows it's the longest dimension of the physical device is the polarization. They have many, many antennas inside that can act as one. So if you only have one transmission polarization, then there's obviously a probability that they will completely be orthogonal and you'll get very bad power transfer. So if you have an element of energy in the vertical and horizontal, and they have to be from the same source, because obviously they have to travel the same distance. But as long as you have energy in both horizontal and vertical, then some of that energy will align perfectly with the polarization of your receiving device. So that just means you don't have the kind of the holes where you will get this non-alignment of polarization. So again, that will improve the system response for mobile. And in terms of timescales, as I said, from analog to digital switch off is typically 10 to 15 years of the sort of timescales that have been looked at. So I wouldn't like to hazard a guess how quickly from ATSC1 to ATSC3, as we haven't quite even got a standard out, but you've got to figure it's going to be many years. We're going to do the repack first, and I hope maybe ATSC3 is probably going to come up right in the middle of the repack. So obviously many people are thinking, well, can they combine the two solutions, which is relatively smart. Of course, you have to pay for the extra bit, but still, in terms of time, it's probably better to do it now than wait. But again, one of the issues is you've got to dual cast these two things. How long are you going to wait until you turn ATSC1 off? How much legacy equipment is out there that you've got to support before you feel comfortable that you can make that switch? And so all of these things are certainly implementation and planning issues. But I think that the thing here is having a system that's very broadband, which will allow you to share with what would traditionally be your competitor, which is maybe the guy that has the tower a couple of 100 feet down the road, is maybe not your competitor anymore. It's probably the likes of T-Mobile and AT&T and the cellular boys who are, let's be fair, they're rolling out networks in the space that we've just vacated, doing something very similar to what ATSC3 allows us to do, which is really transmit data to lots of people. So as broadcasters, as we lose our spectrum and get squashed, having the ability and having systems that will allow you to help your neighbor and them to help you is probably going to help the industry as a whole. And that's a relatively new concept to US broadcasting, but for many broadcasters in the world, they often are a bit of a monopoly and they have many channels at their disposal, and financially it makes a lot more sense to have combined systems. You have one tower and you'll put as many channels into that given system as you can, because it's a cheaper way of doing it. Obviously if you're competition, there's some issues within separate companies, but you can see there's a lot of consolidation in the industry as well. And so buying systems that are broadband will allow you to take full advantage of that. And that's maybe the key thing. We need to take full advantage of ATSC3 as an industry, so that we don't get left behind. So that's the kind of technical bit. So from that technical and kind of what that means and where we've used it, I just want to show some experiences and why we used particular equipment in given cases. So this was a case in Latin America, where often customers internationally, they have a frequency, but they don't really know what frequency they're going to be on, and that, you know, they may know, they may not know, and often they ask us what it is. You know, it's kind of potentially a lot less regulated, and it might be sometimes they ask us, well, what frequency is good? You know, so they can sometimes not know essentially what channel they're on, and they also might not know how many channels they can even get. So having a broadband system means that it's a lot more flexible in terms of what they end up with. This was a system that they also was elliptically polarized because they wanted an element of V to cover mobile systems. And again, this is a broadband thing. The interesting thing about this particular product, and I'll go on to the next slide, is it's essentially the same product, is this is a slot antenna. So this is a standard design coaxial slot antenna, but this is a very broadband device. As we know, most slot antennas traditionally that we've seen is single channel. If people said they were broadband, they were 2, maybe 2.5 channels wide, you know, 12 megahertz. So you can see here from the plot, this is a broadband slot antenna, actually one that we produced this year, but this one, it's very hard to see, but this one was produced over, you know, almost 10 years ago, 2008 this plot is from, you can see the date on the plot. This one was in May this year. And this antenna is covering every single repack channel. It's 14 to 36, but it's still a slot antenna. So again, I was alluding to having a broadband antenna gives you flexibility in the future, but then you've also got a tower loading problem. So a big panel array, that's great, but now it doesn't fit on your tower. So this is a product where you have the benefits of low wind loading, low weight, relatively easy installation, so it's quicker installation, but it's also a very broadband product, so it doesn't matter what frequency you have. And this is a product that's we've been doing for many years, as I said, about 15 years. This can be used for an auxiliary antenna, so maybe you want to put an aux up, but you want to allow some other broadcasters in the area to use that because it's a backup and you can all share the cost of that if that's not going to be refunded. Or maybe if you are being refunded, you can use it as an aux straight up. But it's also perfectly good to use as a main antenna. And you have the Azimuth Pattern choices of a typical slot antenna as well, directional, omnidirectional. So this is a product that we've used internationally for many years, but we feel here, particularly for the repack, it should be you know, a very choice product for broadcasters. Again, this is Latin America again, as well as the antenna. There's also combining systems. So this is a typical combiner that's used internationally. This is a system that we did about 10 years ago in Jakarta in Indonesia. Some people I've read said that as a company we don't do high power. Well, I would say that this is a fairly high power system. This was a 400 meter, 1,300 foot structure. with a large panel array. So this was a panel, not a slot antenna, but that's just what the requirement needed. And this is, as total power is 5 channels. This antenna is transmitting 320 kilowatts of transmitter power. Some of those channels are analog, but some of them are digital as well. I think there was 3 digital and 2 analog. With one channel, I think, was 180 kilowatts. That was one of the analogs. And to give you an idea, the ERP on this antenna was almost 10 megawatts. So this is very high power, large structure, large combiner system. So we've done, and this is digital and analog, so we've done some very high power systems around the world as well. This is a project, this was an AlanDick project that was done in Vietnam, in Ho Chi Minh City. I get to climb occasionally, get on top of the antennas to check that they're okay. In my younger, slimmer days, I don't know if I'd fit up the spine anymore, to be honest. But you know, this is again a combined system, analog and digital frequencies. Even in Korea, this was a system we did in 2001. It was actually an 8-panel system. It actually looks like an 8-panel system. It's actually 4 separate antennas. There's actually 2 KBS, 1 MBC, and 1 SBS. It's on Namsan, which is in the middle of Seoul. I believe, I don't actually know for sure, but I believe that this is probably being used for ATSC3 now. We didn't do anything to the antenna. It was ATSC1, and it's in a location where, with ATSC3 that they put on in Korea, that they've actually done. We didn't have to do anything, and honestly, I don't think we were even contacted. There's no real change from this particular system. It wasn't highly flexible. The interesting thing about this particular antenna is you can see the picture on the bottom left is the revolving restaurant view. That was the view from sitting on top of the antenna, and it was the only time I've commissioned an antenna where I had an audience looking at me. And these are some of the projects we've done in the UK. Now, the interesting thing here is not the antenna on the top, which is, again, a fairly standard panel antenna, is the antenna that's lower down with the many panels, but we call that a wraparound antenna. This was done because the tower's too big and it's the wrong size. But the key thing in the UK, probably the most important thing is the pattern performance, particularly the Azimuth pattern. It's a small island. No matter where you put an antenna, or nearly no matter where you put an antenna, you're interfering with somebody overseas. And so there's always, you're never really allowed to do a perfectly omnidirectional pattern. But that means that on the angles that you need to reduce your power, they want those to be as small as possible so that the rest of the signal is very good. And so the pattern performance was very critical. They didn't really care even that much about impedance. It had to work. And you could see they didn't really care about loading either, but the pattern performance was very much their number one thing. And the idea of the antenna lower down, that is actually the backup antenna. That's the reserve antenna for the antenna on top. So they spent probably 5 times as much on the reserve antenna as they did on the main antenna, because that's how they had to do things. And the idea was the pattern of the reserve would, as closely as possible, copy the pattern of the top. And this wasn't a one-off. There was probably 15 or 20 sites in the UK that use these large wraparound antennas. And during the analog to digital transition, those antennas were probably transmitting 5 analog frequencies and 6 digital frequencies at the same time. So you'd have a 11-channel combiner. It was the first antenna they installed, so the original antenna would be on top in the prime position, as you expect. The reserve antenna, the wraparound, was installed first. All the services were put to that, so the top antenna was turned off, and then you could replace that with the final solution in a phased change, putting the auxiliary up and then putting the main up, which maybe again is something that during the implementation phase of the repack, again, auxiliary antennas, putting something up, you might not want to spend quite as much money on a backup antenna, but you know, that's some of the things that we've been involved with. Also projects in the US, so we have been involved in some of the more recent large projects in the US. This is in New York, where a channel 3 antenna, but this was a circularly polarized channel 3 antenna. It's actually the very top antenna on that picture. And the key thing of this, it's circularly polarized, it's low band. It can be band 1 or band 3, but the weight and wind load of this is actually pretty small. It's probably equivalent to the same size batwing antenna but it's circularly polarized. So if you need a low wind load, okay, you have to top mount it by and large. Okay, you can side mount it, but it's a very omnidirectional azimuth pattern. So if you need a circularly polarized, very omnidirectional azimuth pattern, but with a relatively low wind load for a band 1. Now you have to remember band 1 is huge. The antennas are huge. This is a very good solution, and we have a reference here in New York. And we've done stuff in Toronto on the CN Tower. This was an AlanDick project from many years ago, a large radome. So that's some of the worldwide experiences. Just to kind of focus on SFNs and to kind of finish my presentation. This is a project we've done in Singapore. This is actually still an ongoing project, which surprises me. We did the main site in 2013, and then after that, and the main site is a fairly typical, or I would say international antenna. It's broadband, it's a panel antenna, it has many channels going into it. But what they wanted to do in Singapore is to fill all the gaps. And they had a mandate where they really wanted to cover, I guess, indoor rabbit ear type reception, which is, again, very typical to the second television, the third television, the fourth television. So the main site is, a reasonable sized tower, 12 panel, 24 lambda panel array that we, as I said, we did in 2013, typical sort of power. We also provided the channel combining system here. This was a channel combiner mask, so the transmitters had no output mask filter. The mask filter was part of the combiner. The filter. These were 8-section cross-coupled filters to provide adjacent channel combining and critical mask. If you're, by and large, okay, maybe channel 14 is a bit different, but by and large, if you're combining adjacent channels and the mask, the filter's the same thing. So why put 2 in the system and have double the loss when you can do it with 1? So you can see here, this was combining 6 frequencies, 3 were completely adjacent, but the customer wanted the ability to actually cover pretty much any channel from 21 up to a 39 or 40, and have up to 10 channels in the future. And so that we didn't know what the future channels were going to be, whether they were going to be adjacent or non-adjacent. So the combiner, every channel had the ability to be an adjacent channel combining, whether it was adjacent or not. And we've actually since gone back and added a 7th channel to this. I think it might have been 37, so that was adjacent to one of the 38. So in combining the mask filter and the combiner, you have a very low loss design. These are waveguide filters, maybe 0.25 dB loss on a given module, and so that's your entire loss combining and mask filtering, which is pretty good as a total system. So as I said, whilst that was an interesting project, that was not really the main thing. So this is where the main site is in Singapore. Singapore's not a geographically large area. It's about 50 kilometers by 30, so 30 miles by 20 miles. It's the size of a typical city here in the US, probably smaller than a lot of them. It does have a lot of high-rise buildings, but then that's not unusual in large cities as well around the world. So this is where the main site is, and the goal was to cover the areas, particularly where there was a lot of large buildings, and so you have a lot of shadowing from the main site. So we looked at putting 10 repeater sites in. In fact, these sites were actually, they weren't off-air repeaters, they were basically low-power transmitters that are synchronized. And again, using DVB-T or T2, which this was, the SFN part of this, whilst you have network issues, so you have to get the timing right so that the signals don't interfere with each other, but they work with each other, the RF issue is less of an issue. You're kind of changing the engineering headaches from purely an RF issue in the good old analog days to now you still need RF because you've got no RF, you have nothing to work with, but now you have a network issue as well. So from a broadcast engineering point of view, that's a different thing to worry about, something that we haven't had to worry about in the US so recently. But with DVB-T and ISDB3, the way the standard's written is very much allows you to kind of switch that on in a relatively thoughtless way. that's maybe oversimplifying quite a lot. But in comparison, you kind of switch it on and it works. And the thing to know, it's not like an FM single frequency network where what you're really doing there, it's not synchronized. It's an analog synchronization where all you're really trying to do is you're trying to map the coverage so they don't overlap. Here, you want the signals to overlap. As long as you have enough time, more overlapping's good. So it's digitally synchronized, which is even different to the way ATSC1 does it, which is an 8 VSB signal. Whilst it's a digital signal, the synchronization is very much analog. So the SFN side of it is different, but it's better. It works a lot better. So we put on 10 stations, and they actually find there's still far too much shattering, even though they're all dotted around this relatively small landmass. So they required more sites. Now, to give you an idea, we started this project in 2014. We're still working on this project 3 and a bit years later. And in terms of the number of antenna sites or antenna transmission points that they now have now, we're now done 180 different antennas. You can see where the red dots are located. That tends to be where the higher density of buildings are, particularly where they call them HDB blocks, the housing development blocks, which is where many people live. They're 30-story high buildings with large population, and they're built quite close together, so you have a lot of shattering. But this is a real-life example of how an SFN could be used, but it is covering in-building coverage and a high level of coverage, which with just one site, it's just not achievable. And in terms of what these antennas were at a given site, the antenna side of things were relatively simple. This was one of the larger ones. This has 6 panels. To get some economies of scale, the broadcaster in Singapore had 4 RF channels combined at each site. So they had, and they're 8 megahertz channels, so they had 32 megahertz of bandwidth, RF bandwidth being used, which lowers the cost, because instead of having 180 individual sites is expensive. If you're sharing 4 ways, then the cost becomes, again, more practical. And this is what a typical site would look like. It's mounted on the side of a building. It covers 180 degrees, and relatively low gain. Some of the sites were a single panel. I think the site with the most panels was 16. There was only one of those. This was a typical site, 6 panels, 4 panels. So the antenna side of things is relatively simple, but the thing to note is the quantity, obviously. And it very much looks like a cellular installation network, which is maybe not surprising because it's using essentially the same modulation standard, and it's trying to do pretty much the same thing. So none of this should be, when you look at it like that, it shouldn't really be a surprise. But a lot of broadcasters are going, wow, that many sites, that's really unusual. Well, it's what the technology leads us to do. But this is just real life proof that this is what works and this is what's done. And that's kind of what it looks like. And in terms of, we've supplied many panels in this system, probably one of the largest SFNs in the world. That was mainly because of the buildings that were there and the shattering, and also the goal of trying to get in-building coverage. We've seen we need not a lot higher signal strength or a lot more sites to do that. If you're really only interested in less mobile or less indoors, then you probably don't need 180 sites, but you might still want to look at 10, 20 sites or something like that, depending on what your goals are. But within the standard, as I said, you have different audiences. It's up to you as broadcasters to find the business case. As long as the regulation allows you to maximize the use of the technology, then you as broadcasters have this choice. But in terms of a supplier, we've been working in this field for 20 years, so we can help you because we've gone through any pain that was involved. And that's pretty much the end of the presentation.